So section 5.4 is about power. Okay, is about power. And the idea behind power is this. The amount of work some person or object or machine does can vary as a function of, as a function of where it moves from location to location. For example, if I were on the bottom floor and I started jogging upstairs, if I go to the second floor, I change a certain amount of potential energy, so I do some work. Or if I go to the third floor, I do more work to run up to the third floor. To run from the bottom floor to the fourth floor, I do even more work. Now, if two people were on the ground floor, all right, let's say hypothetically it's me and Jenny, I'm using an example. And Jenny starts to jog up the stairs, whereas I'm just walking slowly, okay? But she makes it to the fourth floor, and then a few minutes or a minute later, I make it to the fourth floor. We both do the same amount of work, but the amount of power generated is different. Power is a rate, like velocity. So if I walk from this side of the building or this side of the room to that side of the room, it's a given displacement. Now, if I walk faster, the displacement is still the same, but the velocity is what changes. So if I walk really slowly, my velocity is a low number across the whole room. But if I jog across the room, my velocity is faster. It's a rate of change. That's what power is analogous to. So, although two people might perform the same job, if one does that job quicker than the other, it means they generate more power. So, another example would be like, imagine a horse and buggy. So, a horse, and this is where power starts from, horsepower. We'll talk about that today as well. A horse is pulling a cart behind it, and another horse is doing the same thing. They both go the same distance, but one horse goes much faster than the other. The horse that went faster generated more power. So power is really defined as the rate at which work is done. If you do work faster, you're generating more power. And we're going to see that now in this next slide from our definition. So let's take a look at our definition. But again, power is the rate at which work is done. Or, if you think about work, work is energy. The rate at which energy is transferred. All right? The rate at which work is done or at which energy is transferred. Now, you'll see that there's two formulas there. We could start by saying, well, power is the rate that energy is transferred. That's this right here. Power equals change in energy over time. Or, power equals the amount of work done over time. Either of these is acceptable, depending on the problem. So if you know in a problem you're given like a force and a distance, you can do force times distance to get the work done, divided by time. If you don't know anything about a force, but you know that, say somebody started at the ground floor and went up to the third floor, you can find the change in energy. Right? Energy level at ground floor is 0 for potential energy, and then the energy level at the third floor, potential energy, find that delta or the change in energy and use the first formula. So either of those two formulas work for this instance. Now, what we can also do is this. I'll go into the units in a moment. But what we can also do is this. We can start by remembering, if we look at this definition, we can replace work with F d cosine theta, which is really the definition of work. Work is force times distance times the cosine of theta. Now, for all of these problems for power, we're going to be looking at one-dimensional motion. So theta turns out to be 0 in this case. So imagine again you push on a desk, I'm pushing to the right, and the desk moves to the right. Theta is 0. I'm lifting an object off the ground. I'm lifting it off the ground vertically, and it's moving vertically. So I'm assuming that there's no angle theta in these problems. Theta is 0. So if we remember from, like a week or two ago, cosine of 0 just becomes 1. So this becomes force times distance over time. But what's distance over time? What's distance over time? Speed. Very good, Jake. Speed. So in reality, power is really also known as force times speed. If we're only moving in one direction, say to the right, we can use velocity instead of speed. So the formula you're going to see on your formula sheet for this is as follows. Okay, so either that one at the bottom or one of these two at the top. So when it comes to power, we're going to be able to think about three different equations. Power equals change in energy over time. Power equals work over time. Power equals force times speed. Now, this last one, it's important to jot this down. In this scenario, both speed and force are constant. They're not changing. So if the velocity of an object is moving but it's changing as a function of time, you can't use this definition. Okay, so this is when you have a constant force and velocity, both. When both the force and velocity are constant. Now let's take a look at our units. Let's go back up. The units for work or energy are joules, as we've seen in sections 5.1 through 5.3. The units for time are seconds. A joule per second is known as a watt. Okay, a joule per second is called a watt. W-A-T-T, abbreviated with a capital W, not to be confused with this W here for work. This W will always appear after a number, like 37 watts. So you'll see it as a unit, as opposed to seeing this W in the formula.
Would you rather us use joules per second or W?
Use W, use watts, yeah. Power ratings anywhere are known as watts, okay? Now, where have you heard the term watts before? Where have you heard watts? In light bulbs, yeah, definitely. You've seen watts in light bulbs. On the bulb it says 60 watts, 40 watts, whatever it is. So when we get to electricity in the second semester and magnetism, we're going to study electrical power. It's analogous to regular power here. So the power you generate here is mechanical power. So imagine that energy goes out at home, right? And you have to crank a generator. So you sit there like a lawnmower and you pull on that hand crank just to get it going, and then there's a certain amount of fuel in the generator, and that fuel is converted to electric power. So by pulling on the crank, I'm exerting mechanical, or doing mechanical work, in essence using mechanical power. Now once the motor starts going, and the chemical in the battery starts converting to electrical current, now that's electrical power. But power is still power. It's still both measured in watts. So although we're looking from a mechanical point of view, as we get later in the year, we're going to look from an electrical point of view, still though using units of watts. Now, the term power, before watts were really used, what were the units for power? Anybody know back in the day? Think about what generated power, what animals were used for power. Horsepower. Okay, and here's how it worked. This is kind of an interesting fun fact, a little historical fact for you. So, the way a horsepower was determined, it was the amount of coal that a horse could pull out of a coal shaft at a certain velocity. And it was really a pony actually that was used. Okay, and that's what was represented by 1 horsepower. And it was like an average that was taken. Then the term watts was introduced by scientists. What's Watt's first name? Anybody know? J.J. Watts?
No, J.J. Watts.
J.J.
Watts is the NFL player.
Oh, I think you're serious for a second. But the scientist with the last name of Watt or Watts, I forget what his first name was. I'm sure I'm blanking for it. Well, he introduced the unit of watts, and then came up with a conversion between horsepower and watts. And the general conversion, and I forget the actual number. What's the number? 745, I think. Can somebody Google that?
His name's James.
James Watts? James?
You're welcome.
Can we Google horsepower to watts real quick? What is the conversion there? 1 horsepower equals how many watts? I think it's 745 or 749.
745.69.
All right. So if we rounded 745.7?
0.69, yes.
All right. So the units of watts are actually a rather small unit if you think about it, just like we talked about with joules and calories, right? So 1 horse, average horse, right? Again, horses have different strengths and they run at different velocities and everything, but 1 horsepower equivalent is 745 watts. So when you're thinking about cars, they talk about horsepower, and they say like an engine can provide up to like 400 horsepower. It'd be like the equivalent of 400 horses pulling you forward. That much work being done on the car is being generated by the engine. So when we do this in a moment, we're going to look at an example of horses and try and come up with the conversion in that problem. All right? So let's look at the first example.
Two horses pull a cart. Each exerts a force of 250 newtons at a speed of 2 meters per second for 10 minutes. Calculate the power delivered by the horse. How much work is done by 2%?
So we've got two horses pulling on the same cart. So if I were to visualize this, this is what I'm seeing. Bird's eye view, maybe. All right, so there's the horses pulling like that with 250 newtons of force on the cart. So what is that really the equivalent of? How might you approach this problem? If you have two horses, each pulling at 250 newtons, what is that the equivalent really of?
700.
Not 700, but
Oh, 500.
500, yes. Very good, Victoria. All right, so I would start by saying that it's really like one horse pulling at 500 newtons of force. Now, we're also told in this problem that we're given a speed that the horses move at 2 meters per second. That's a pretty slow speed. And think about it for a second. Ready? I'm going to demonstrate 1 meter per second. And you could always think about this visually. Take a step, a big step, of about a meter every second. So this is about 1 meter per second. Okay, whenever you forget what velocities or speeds are, relatively speaking. So 2 meters per second is not very fast. Humans can easily run at 2 meters per second. So this is like, a horse barely trotting. They might as well be walking with the strides the horses have. This is probably a normal stride for a horse, almost 2 meters when they take a stride. Probably less, obviously. For 10 minutes. Okay, for 10 minutes. Now, we want to determine how much power is delivered by the horses in that 10-minute period. That's the first thing we're going to figure out. So, we've got an overall force of 500 newtons. We've got a velocity of 2 meters per second. We've got a time period of 10 minutes. What's 10 minutes really, though? What do I want to make that?
Second.
Yeah, good. Seconds, because I'm in meters per second, right? So 10 minutes, there's 60 seconds in a minute, 600 seconds. Okay, no need for dimensional analysis for something simple like that, right? Realize that 60 seconds a minute, 60 times 10 is 600 seconds. Now, since the time period is 600 seconds, we know that we're going to be looking at rate of change. We're trying to find the power delivered. And we have three options for formulas. So we've got power equals change in energy over time, or power equals work over time, or power equals force times velocity. Which of these three formulas are we going to use for part A? For part A. Marianne? Yeah, how come? Yeah, I would use this one right here. Power equals force times velocity for part A. So let's go ahead and do that. The overall force applied, again, is 500 newtons times a velocity of 2 meters per second, making it a simple 1,000 watts. Okay, 1,000 watts. Now, before I go to part B, let's go back to that conversion a minute ago. We said that a horsepower, the equivalent of 1 horsepower, was 746 watts around. So 2 horsepower would be like 1,500 watts. So are these horses working to their full potential? They're clearly not. Right? And that's what we can see by the velocity really as well. Had they been running a little bit faster, velocity would be higher, this number would be higher. Okay? So it really depends on the scenario we're looking at. So 1,000 watts of power are delivered by the 2 horses. The follow-up, part B, says how much work is done. How much work is done by the 2 horses? What can I do for this part? If I want to find the work done. Ed, what do you got?
You could plug in P is equal to W over T, and then you have your so this be 1,000 times 2.
Yeah, so let's take, not 2, but let's take a look at what we're going to have there. We have power times time equals work done. So it's power, which is 1,000.
600.
Yeah, there you go.
Work is equal to power, right?
work is equal to force times distance times cosine theta. Power is equal to work over time.
Okay.
Okay? Power is work as a rate of change. How much work is done in a given time period. This, again, this W is work.
Oh, it's because we have.
This W is
Yeah.
watts. It's, remember, units are
Right,
different.
right.
If it's in a formula, it's work. If it's after a number, it's units of watts. So the amount of work done, 600 times 1,000, therefore, 6 what?
No.
600,000.
Well, just, yeah, put the words together, 600,000, and an extra zero. All right, 600,000 joules of work. Let me just do it this way, right? 600,000. So if you were maybe taking a multiple choice question, this was a question, it'd probably be written in kilowatts or kilojoules. So you might see this. Work done equals 600 kilojoules. Just to be familiar with that, so we know that we can easily convert. Because remember, we always get answers that are very large in energy levels, because joules are a very, very small unit of measurement. Okay, so your answers usually going to be rather large numbers. Any questions on this one so far? Let's try number 2. So example 2 says how much power is needed to lift an elevator with a mass of 500 kilograms. This is pretty reasonable. It's about 1,200 pounds. It's about the mass of an elevator, the weight of an elevator. If it travels at a constant rate, which is not really true, okay, it really does kind of speed up and then slow down, but we can come up with like an average rate, over a vertical distance of 100 meters in a time period of 15 seconds. 100 meters, that's around 300, okay, around 300 feet. It's not the same, obviously. 100 yards would really be 300 feet. But if you want to get an idea, that's like 10 floors. Once the elevator starts moving, if it doesn't stop along the way, about 15 seconds it can cover 10 floors for a quick elevator. Maybe like an old elevator in a building in the city would take much longer. And it would generate much less power. Okay? So let's talk about this for a second before I go into the problem. Let's quickly discuss something. Take a look at this formula for a second. And realize 2 things. The faster something is completed, the more power there is generated. And that's indicated by the formula. T is in the denominator. So time is indirectly related to power, inversely related. So as the time it takes to complete a task goes up, it means you have less power. Power goes down. If the time it takes to complete a task goes down, power goes up. Okay, we can see how those are inversely related. So we'll see that in this problem here. Now, I can use that formula. Guys, you need to focus. Some of you are losing focus, please. I can use any of those 3 formulas. Which of them should I, or could I use? I mean, theoretically you could use any of them, but which of them is easiest to use? Yeah, should I, could I, will I? Any of them could be used, so I don't want to say you could. You could use any of them. One is better than the other, though. Work over time. Why work over time?
Because you have to work with 500 grams, 500 kilograms on your 100 meters.
All right, so let's use work over time as our first one. That works? What's the definition? Mike, stop. What's the definition for work?
Force times distance.
F,
Oh, F times D times force.
good. Over time. Now the question in this problem is, what's the force, though? That's the only thing you got to think about first. And you could use this method. What is the force that the elevator cable is exerting on the elevator to pull it up? It's not in the problem. The force is not there. Physically, what is the force? What force is the elevator cable combating?
Gravity.
Gravity. Gravity wants to pull the elevator down, like the elevator cart down. The cable pulls it up. So gravity is really the force that's existing here. So this is really Fg, right? Gravity. So put a little g right here. force of gravity. But Fg equals, fill in the blank, M, yeah, Ma or Mg, either one works really, equals Mg times d times cosine theta all over time. The cable is pulling up, the elevator is moving up, so theta is 0, so that part doesn't matter because the cosine of 0 is 1. So that part drops off. So we get mass times gravity times the distance traveled all over time. Now, please pause for a second. Don't actually do the work yet. Because we could plug in. We know mass, we know gravity, we know the distance traveled, we know the time. Second formula. Let's use this. So we use this one so far. Let's use this one now. Power equals change in energy over time. This one might be easier for some people to use. What kind of energy is changing in this problem? The elevator starts here at rest. It moves. And it stops here at rest. What kind of energy is changing in this problem? What kind of energy? What is it? Potential energy. So, although I see delta E, the energy that's really changing is potential. So I'm going to write delta PE. So that delta E is really just saying some change in energy. Which is it? You have to use the context of the problem to figure it out. Well, change in potential energy means PE final minus PE initial. Now, it might be confusing if you don't have a diagram. So maybe you want to draw a little diagram over here of an elevator moving up. And this is where the elevator is going to stop. And what will I call this right here? What am I going to call this, what I'm drawing in, that red horizontal line? Yeah, ground level. Why is it useful to call the beginning of the problem ground level? Who can remember from potential energy and conservation of energy? And remember that skate park ramp thing? We had to move the potential energy reference line up to the bottom of the ramp. Why is it useful?
Because if it's not directly at the bottom, then it has both potential and kinetic.
Yeah, well, not both potential and kinetic, both initial and final.
Yeah, sorry.
If it's starting at ground level, that means the initial height is 0. So this drops off. That's why we call where the elevator starts ground level. If it starts here and you're calling this 0 height, well, initially this is going to be 0 because remember, potential energy is a function of height. If there's no height to start, there's no potential energy to start. So in the beginning of this problem, there is no potential energy. Then it moves up to a height that's 100 meters higher than where it is, which has some potential energy. Well, the formula is going to be the exact same answer as we got up here. Keep this formula right here. Okay, keep that formula in the top right in mind. And think about PEF. PEF is really, potential energy is mgyf over time. But it's the same exact thing. What's YF in this problem?
D.
It's D. It's the same thing. YF is the final height. Well, the final height was 100 meters above the bottom height. So whether you call it YF or call it D, either way, you're plugging in 100. 100 meters either for YF or for D. It's the exact same answer. So either approach works in this problem. Even the third equation would work, but I'm not even going to go into that one. Because then I have to calculate the velocity and such. So I'm not going to go into the third one there. Right? It doesn't make sense to use it. I wouldn't use it. I would use one of these two. So at this point in time, either one gives you the same answer. Okay, mass, what did I say, 500 kilograms times gravity times the final height or the distance traveled. Either way, it's 100 meters over 15 seconds. And what do you get as an answer? It should be in the like 30-something thousand, right? Jen?
32,700 watts.
Yeah. 32,700 watts. Now, I'm curious, would horses be able to lift people up at this rate for that distance? So let's take 32,700 watts and divide it by 745. Because that's how many watts are in a horsepower. Let's take that answer and convert this to horsepower by dividing by 745.7. Whatever. What do we get for power in horsepower?
43.89.
So think about this for a sec, guys. If we didn't have electricity, if we didn't know how to work mechanical operations, and we were still using horses to... Anybody watch Game of Thrones or a show like that where they have a lot of like crankshafts? You know what Game of Thrones, like the wall, and they always have to raise and lower things, and they're always turning a crank? Think about how unreasonable that actually is in the show. It would take 44 horses, the equivalent of 44 horsepower, to move somebody up that fast. So either it would work still, it would just take all day. It might not be 15 seconds, but maybe imagine now it took like an hour to lift somebody that far up by using a crankshaft. It's a person standing there doing this. Okay? They'd have to turn for like an hour to get someone to move up that far. Whereas horses, 44 horses, could do that in 15 seconds. Either way, we're not going to use horses or manpower. We use electrical power to do that. All right?
Where did you get that 100 from? Next to Bradley?
That's the final height of the object, or the distance traveled. Either from this, you plug it in for D right there, and that goes right there, or for YF, and it's 100. I think in the problem it said 100 meters, yeah. Yep. Okay? So again, just to give you an idea of what your answers are equivalent of. So you have some number sense as to what the numbers actually mean. Because 32,700 watts doesn't really tell me too much.
Well, we have to put a horsepower on a test and
If I give you the equivalent, if I give you the constant and say, you know, if one horsepower equals 745.9 watts, how many horses would this be equivalent to? Or just give an idea of that. You'd be given the constant, though. You don't have to memorize it, okay? All right. Can I get someone to read, please, nice and loud?
If a car with a mass of 1,800 kilograms accelerates from a velocity in a straight line of 3 meters per second to 10 meters per second in 15 seconds, then what is the average power delivered by the car's engine?
Now, first of all, let's discuss the beginning of this problem. What's 10 meters per second? Somebody convert miles per hour. What's 10 meters per second? Use Google if you like. Okay, 10 meters per second to miles per hour. Just so you get an idea of whether or not this is a problem where a car is moving fast or slow compared to what we know. What do you got?
22.369 miles per hour.
What is it? Oh,
22.4 miles per hour.
22.4. Do others agree with that? 10 meters per second gives you 22.4 miles per hour.
That's what it says.
I don't know, I may put my, I got 4.4.
I got the same thing. You got mine?
Got my total.
Yeah.
I don't know.
and you
Let me see what you did.
And it could be even just not.
Meters per second, you have the 2. Because somebody did it last class, got the same answer. They must have made the same mistake.
suggested, that's why.
All right, so let's go through some reasonable sense of this problem. So 3 meters per second is like a third of that. So you're going from 7 miles per hour to 22 miles per hour. 7 miles per hour, which is like, what is that? That's like coasting, right? It's like you have your foot off the brake, but you're not pressing the gas. The car moves at like 3 or 4 miles per hour still. Maybe like a small rolling, like you're just leaving a stop sign. And then you're going up to 20 miles an hour through like a residential neighborhood. First of all, would it take you 15 seconds to do that? Probably not. You'd have a really light foot if you did. Like to go from 7 miles an hour to 22 miles an hour, it probably wouldn't take you 15 seconds. It would take you much less time. So if it takes you 15 seconds, this is very not powerful, or the engine is not powerful in this case. If it took you something like 3 seconds, which it probably would, that's a little bit more powerful because it takes less time. So we're not going to get a large answer as far as power is concerned in this problem. Let's keep that in the back of our head. All right, so now let's begin the idea. So we have a mass of 1,800. We've got an initial velocity of 3 meters per second, a final velocity of 10 meters per second, and we've got a time period of 15 seconds. Now, again, 3 formulas. Work over time, change in energy over time, force times speed. Which formula will I definitely not use? There's one that stands out right away that you know you won't use. Work over time. Why not work over time? Yeah, you don't have the work in this problem, right? You're not given anything about a force times the distance or anything at all. So we're not going to necessarily use work over time. What's the other one we're not going to use? Jake?
Force times.
Yeah. We're not given anything with a constant velocity, remember? That was the stipulation I made when we derived that formula. The stipulation was that force and velocity are constants when that happens. So we're not really going to be using that one either. Now, I can indirectly use work, and I'll explain where it's a little bit confusing, but the best one to probably use would be this one here. What kind of energy is in this problem? Kinetic. How do you know that, Victoria? Because it's moving. It's moving, and then it's still moving at the end. It started at 3 meters per second. It ended at 10 meters per second. So there's some sort of motion. So it's kinetic energy. So in this problem, I could start by doing this. I could say, well, the change is kinetic energy, right? Now, if you wanted to, you could have recalled that work could also be defined as the change in kinetic energy. Remember the work kinetic energy theorem? That was from section 5.2. The work kinetic energy theorem told me that the work done on an object is equal to its change in kinetic energy if it's moving along a flat surface. So I could have used work over time, but then you have to remember that work equals delta KE. So personally, I would have considered, as Marianne said, the middle one. All right, and looking at the change in energy. But it's really the same answer either way. So let's go to this problem now. Let's take a look. So change means final minus initial. And then I throw in my formulas. Kinetic energy. What's the formula for kinetic energy? 1/2 mv squared. And I'm going to put Vf squared for final. The mass is constant. It's not changing. It's not like we have a rocket where it's burning rocket fuel or something. So I can leave mass as just m. At this point, I could plug in, or I could simplify a little further. For those that like to come up with a better expression, what could you take out of the numerator and put out in front? Not, be careful, don't say cancel. It's not in every term. You have to, what's the word when you pull it out front? Take out the mathematical. There's a term when you take something out of every term. It's called the what? There's an acronym, the blank, blank, blank. What is it? GCF, the greatest common factor. So you can't cancel mass here. Be careful saying that.
So we should just include it then, right?
So it looks like this. Ready? Okay? That's what I was getting at. All over time. Again, you don't need to do that. You could have plugged in right here. You know all these numbers. You can plug in. Personally, I like things to be simplest in variables first before I plug in. This is simpler than this. That's why I factored out a 1/2 m.
Yeah.
Okay? Remember, Jake, the reason you can't cancel m is because there's no m on the left-hand side.
Oh,
If this had been power times mass somehow, I don't know what it'd be.
Because if you do a mechanical energy problem,
They happen to drop off. Yes, very good. I'm glad you picked up on that, though. See what Jake picked up on with the conservation of energy problems. When there's potential and kinetic energy, a lot of the time mass cancels from everything because it's on the left-hand side of the equation and the right-hand side. It's in every term. But here it's not in the term with power, so we can't cancel mass. See how much you're learning about math and algebra?
Yes.
Okay, I keep saying that. By the end of this year, you're going to be like an algebra pro from between your math course and this course. All right, so let's plug in 1/2 of 1800 times 10 squared minus 3 squared all over 15 seconds.
5,000.
5,460. I wrote 640, but I think I wrote it backwards on my sheet. Can somebody check that? Because the other class gave one of those two answers. I felt like I wrote it backwards when I wrote it down.
All of them.
5460.
You got 5,460, right? Okay, so I definitely wrote it backwards in my notes. I wanted to correct that so I knew. So 5,460 units of watts. Now, let's convert that, folks. Let's convert that. What is that in horsepower? So we get an idea of how many horsepower the car is generating by traveling only from about 7 miles an hour to 22 miles an hour. Around 7.3 horsepower. So, let's think about this for a second. Reasons why it's such low horsepower. Reason number one, you're only going from 7 miles an hour to 20 miles an hour. So you're not really changing velocity much. Had the final velocity been larger, say you were going up to like 70 miles an hour, instead of this being a 10, this would be a much bigger number, therefore giving you a much bigger amount of power. Second reason, this is a small horsepower. Time. It would never really take you 15 seconds to go from 7 miles an hour to 22 miles an hour. 15 seconds to do that means you're like literally just touching the gas. You're barely accelerating at all. Alright, if you were really accelerating, you go much quicker. So imagine instead of 15 seconds, you did it in like 3 seconds. Well, you're decreasing the denominator, and these are indirectly related, so as a result, you'd be increasing the power. So instead of dividing by 15, if you divided by 3, this would go up to like, let's see, 27,000 watts of power, and this would go up to like 35 horsepower. So depending on the scenario, your car can deliver more or less horsepower. Usually, when they give a rating for a car's horsepower, they give the maximum horsepower the car can attain, not the horsepower in a given situation. When they tell you, this car's engine can deliver up to 400 horsepower. But that's if you're really putting the pedal to the metal, okay? Not in a scenario like this where you're just lightly accelerating. So I want you to get an idea of the context of numbers so you understand that. All right?
5:30.
What's due on Wednesday?
All problems set.
What's due on Thursday?
5-4.
And you have a test on Thursday, obviously. And then Friday? Okay? Let's recall that information, please. Jot it down if you haven't done it.